Welcome back to the Greater Essex County District School Board calendar, where we are exploring the fundamentals of mathematics. Each month, we are diving into a big idea from the Ministry of Education's Focusing on the Fundamentals of Math, a teacher's guide, and in particular, the tables summarizing the curriculum expectations from our current Ontario mathematics curriculum that have always been and always will be fundamental for developing students' understanding and proficiency in mathematics. This month, we'll dive into recognizing and applying understanding of number properties. But in order to do so, we're going to first focus in on the unit of measure. So let's dive in by considering two quantities that I'll display up on the screen. Which quantity is bigger? Go ahead, take a moment to think about it, but I'm going to cover it up for you to make this a little more challenging. Now, when I do this with groups of students and adults, we can get a variety of responses. Some say that they estimate that there are the same number of dots, so neither quantity is bigger, but rather equivalent. While they be close, there's actually one more dot on the left than on the right. Others say the dots on the right actually cover more area, and thus the quantity on the right is physically bigger in that sense. And that makes a lot of sense as well. Some notice that each individual dot on the right is actually a little larger than the dots on the left. They must have better eyes than I do, that's for sure. You could maybe claim that one set of dots is more blue or has a higher saturation of blueness than the others. That might be a stretch. However, if the colors had looked more like this, then they'd probably be right. So why does any of this matter anyway? Well, as you saw in the previous example, if we aren't clear on what attribute we are measuring or what unit we plan to use for measuring, it becomes very difficult to compare quantities. In this video, we're going to deepen our understanding of the unit of measure. And in particular, we're going to dive into why the unit of measure matters. So let's get started by looking at a quantity. Take a moment and pause the video to think about how many squares there are. Go ahead, pause the video now. Okay, what did you come up with? When we ask students and adults this question, my guess would be that most would say 20. And for the majority of my teaching career, I would have been completely fine with that. But what if a student said 5? We'd likely say try again or nice try, or maybe we'd just give a confused look and think to ourselves, oh boy, we better sit down at the guided math table to help this student out. But what if I told you that the student who said 5 was as correct or incorrect as the student who said 20? Now you might be wondering, how could this possibly be? Well, the problem with a response of 20 or a response of 5 is that although they've selected the attribute they want to measure, in this case, how many squares there are in the set, both students have not explicitly articulated the unit of measure they are using to count with. Our assumption when we say 20 is correct is that the student has used a single square as the unit of measure. But until we ask the student who said 5 what unit of measure they're using, we really have no idea whether they are correct or not. Numerical responses alone are simply not good enough, especially as the complexity increases with each passing year in mathematics. If we ask the student who said 5 what unit of measure was used, they might say 4 squares. And in that case, if we count how many groups or units of 4 squares there are, you'll find that there are 5 groups of 4 squares, or 5 fours. This is one of the many examples of how unitizing, the process of creating units to measure quantities with, can lead to a deeper conceptual understanding of mathematics and, over time, more flexibility and fluency with numbers. Okay, Let's have a look at another quantity. Again, without reference to the attribute we're measuring, some might say the answer is 1 or 1 square. And they'd be right. But this time, let's focus on the attribute of area for this rectangle. Right now, we have nothing to reference, and thus measuring would be difficult to communicate. I could visualize a unit in my mind, but then trying to communicate that with you would be extremely difficult as well. So let's toss this in as our unit of measure. I've selected my attribute of area, and I've also selected my unit, which has the same attribute of area. I can now iterate this unit over the quantity to determine how many it will take. It looks like it will take 4 of these green squares to cover the blue square. Had we actually created the green square by partitioning the blue square into 4 equal parts, we could say that our unit of measure is actually 1/4 of the blue square, and thus the measured quantity would be 4/4. Or if we use unit fraction language, we could say 4 1/4 pieces. Now that looks very wordy on the screen. So how you write your unit will be your call. However, when we're using the language of fractions in our classrooms and at home, it's very helpful to reference the unit fraction in our language. 1 1/4, 2 1/4, 3 1/4, 4 1/4, to really promote this idea that part-whole fractions are simply a measure of a certain unit or unit fraction. Okay, are you ready for another? Let's look at a quantity where linear measures seem appropriate. If this is our quantity and this is our unit, how long is the line? Now we could spatially estimate that it would take, say, 5 or maybe 6 or even 7 of that unit to iterate the entirety of the linear quantity to the left. If we actually iterate this little line, we see that it would take 5 little lines. Let's double check here. 1, 2, 3, 4, 5. But then at some point, we realize that it's really hard to communicate with other people if the units of measure we're selecting are all random. We can still use non-standard units, but it's really only helpful to the people who have access to that concrete, tangible, or visual unit. So that's where standard units come in. For example, if I told you that this little line was 1 centimeter, or maybe even 1 inch for our US friends, you'd likely trust me and you'd have a reference point in your mind of what that unit is. And if we iterate this 1 centimeter over the quantity linearly, we get 5 centimeters instead of 5 little lines. Or 5 groups of 1 centimeter. And as an aside, we should remember that the centimeter is a part of the base linear unit in the metric system, the meter. We tend to treat the different standard units within a measurement system like the metric or the imperial systems as if they stand alone. However, all units are iterations or partitions of a base unit for a measurement attribute. For example, in the metric system, the base linear unit is the meter. When we partition the meter into 100 equal parts, we reveal a smaller unit that could just be thought of as 1/100th or 100th of a meter. We're simply iterating that fractional amount of the meter, 1/100th of a meter to be exact, to reveal this quantity. And this quantity that is a standard unit for measuring quantities that are not helpful to measure in meters simply has a nickname called the centimeter, since cent en français means 100. A similar logic can be applied to the word percent or percent. Percent can be thought of a ratio between how much of one quantity you have per 100 of another. Pretty cool stuff. So if we return to the base linear unit of 1 meter and we zoom out really far, we can iterate the meter to create another standard linear unit in the metric system for measuring very long quantities like distances between cities. If we iterate 1 meter 1,000 times, we have yet another standard unit, and we call this unit 1,000 groups of 1 meter. But as you can imagine, that's a little inconvenient, so we give it a nickname. We call it the kilometer, where kilo represents 1,000. Wow, we just tore through a ton about the importance of the unit of measure. So let's quickly recap. Identifying both the attribute of a quantity we want to measure and explicitly selecting a unit of measure with the same attribute are extremely important ideas when it comes to understanding measurement. Through various contexts, we've seen that if we want to measure how many blue dots are in a set, we need to clearly articulate what we're measuring, the number of blue dots, and what unit we're using for our measurement. In this case, 1 blue dot to reveal the measured quantity. Then we are free to compare which quantity has more. If we want to know which quantity of dots is longer, then we can select a linear unit, such as this green rectangle, and iterate that. When we compare, it's easy to see that the quantity in the bottom left is longest, or alternatively, that the quantity in the bottom right is less wide. If we want to measure how much of the screen these dots take up, we can define a square unit like this green square and iterate that over top to reveal the bottom left quantity covers the largest portion of the screen, and it might require the use of a smaller unit of measure to determine whether the top left and bottom right quantities cover the least amount of the screen. So there you have it. We are deep into our Fundamentals of Math video series through the Greater Essex County District School Board calendar. We hope you'll join us in our next video where we'll continue exploring number properties.